The Big Bang Theory has been impacted our understanding of the universe, establishing the foundation for contemporary cosmology grounded on Einstein's theory and what is acknowledged as conventional cosmology during the Big Bang. The cosmic era begins with the Bang. Expansion, the origin of all matter, space and energy around 13.8. This occurrence billions of years ago resulted in the huge cosmos that we now view, but recent advances in cosmology indicate that it is possible that the Big Bang was the ultimate source rather than there may have existed before the Big Bang. That was equally crucial in the formation of the cosmos as we now understand it. It is referred to as the cosmic inflation epoch. Of the most alluring aspects of, according to contemporary cosmology prior to the Big Bang's hot, dense condition, the universe experienced an exceptionally quick, exponential expansion throughout this period. The universe's size grew at an remarkable speed to show how this growth was quite severe. If the cosmos had less mass at the beginning than an atom, it would have grown to a considerable size, more than the whole amount of observable world within a nanosecond, with reference to a millions of millions of millions of millions, millionths of a second. This small span of quick expansion was essential to forming the cosmos. When inflation stopped, the expansion's energy source was sent into space, where it heated up and creating the matter particles that include everything that we see now in many. Inflation is the precursor of what is now known as the Big Bang, but the inflation hypothesis is well acknowledged. There are still many unanswered issues in cosmology, unresolved. For example, we have yet to recognize the factors that caused inflation, how long it lasted, or what prompted it to cease. These are a few of the best things in cosmology. Unresolved issues and their resolution is essential for a more thorough comprehension of the beginnings of the cosmos prior to inflation. The cosmos was a very dense little point of substance that is often called a singularity, and the ensuing expansion eventually resulted in the creation of atoms, stars, galaxies, and molecules. While the notion that the Big Bang marked the start of everything in contemporary cosmology is attractive, suggests a more complex picture. According to theories, the universe experienced a time before to inflation. Following the Big Bang, the universe grew, at least exponentially, increasing in size 80 times. This quick expansion was driven by an unknown energy source that dispersed throughout the empty space. After inflation stopped, that energy was transformed into particles, heating the cosmos, which leads to the hot, dense condition that we refer to as the Big Bang. Despite being chilly and empty, the inflationary stage established the foundation for the development of the cosmos and the material we see, one of the most speculative concepts of today. Within modern cosmology, this theory of everlasting inflation implies that inflation continued everywhere simultaneously rather than it stopped in various areas, resulting in several distinct areas or bubbles, each of it may exist as a separate universe. Indeed, the cosmos would be but one of these patches. In accordance with everlasting inflation, there may be an endless several of these worlds, each with its own collection of scientific principles and constants. This leads to the idea of the multiverse. Our world might be merely one of a large or possibly limitless quantity of universes. If this hypothesis is accurate, may help to understand why life is so ideal, appropriate for our cosmos. In this every conceivable multiverse scenario, there might be a mix of physical laws. In other worlds, we just happen to reside in a place where the circumstances are ideal for the formation of stars and for vital components such as carbon and oxygen to appear, in spite of beliefs like as the multiverse and everlasting inflation. Continuing to speculate, the notion of the inflation itself is backed by the most compelling empirical evidence. The cosmic microwave provides proof. CMBB, the oldest light in the backdrop. The universe in which the CMBB was released. After the Big Bang 380,000 years later, when the cosmos had sufficiently cooled for atoms to exist. To create the cosmos at that moment became clear, and this light has been exploring space ever since. CMBB research allows cosmologists to basically snap a newborn photo of this light provides hints about the cosmos. Early times after the Big Bang. Among the most significant discoveries came from the Planck spacecraft in Europe, satellite that took fine-grained pictures of the CMBB. These pictures revealed a small variations in temperature in the early universe that was consistent with the forecasts created using inflationary theory. Experimental validation reinforces that inflation is more than simply a theory of speculation, but an essential part of our comprehension of the beginnings of the universe. Understanding the Big Bang and its aftermath need merging two of the most crucial Einstein's ideas in contemporary physics: general relativity and quantum theory. General relativity in mechanics explains the extensive framework of the universe, including the actions of quantum planets, stars, and galaxies. Conversely, theory clarifies the behavior of the tiniest particles, scales to respond to the final cosmological inquiries, such as what space and time really are and the location of the. When the cosmos first started, scientists had to create a hypothesis that combines these two structures. Such a cohesive theory might enable us to comprehend not only the large boom, but also the circumstances that resulted in it. Is one unexpected feature of the universe is the biggest in terms of size. There are around 47 billion items that can be seen. Light years from now, this indicates the observable universe is about 94. Initially, this was a billion light-years wide. May seem contradictory in light of the age of the cosmos is merely 13.8 billion years. How can the cosmos that can be seen be greater than the light's range? Trip at that period, the solution is found in. Given that the cosmos has been growing over time as it increases, the separation between items becomes larger and larger the further, more than the amount of light that a given period of time. The majority of experts think the cosmos is far larger than what we can. As of right now, it's feasible that the cosmos as a whole is limitless, and the cosmos that can be seen is only the extent to which the part we can notice is restricted. Light has existed from the beginning of time. There could be several areas of we will never be able to see the cosmos. Although the cosmos may not have any boundaries, the issue still stands. Anything outside of the universe. Most scientists don't believe that. Since the cosmos is endless, there isn't. Even if it didn't end, it would simply keep on indefinitely. If the universe is finite, talking may not make sense about anything outside of the cosmos. It has the characteristics of space and time, therefore the notion of an afterlife may not be physically significant. The idea of beyond the cosmos confronts the very structure of physics as we know it. Given that time and space are characteristics of the cosmos itself, is inquiring as to what is false. Before or outdoors, it might be as pointless as inquiring about the North Pole. Similar inquiries are ongoing. Crucially, they push the limits of human comprehension and motivation. Latest scientific breakthroughs, the development of theoretical physics, has resulted in fresh ideas meant to clarify. One such framework is these profound puzzles. According to string theory, the essential components of the cosmos is made up of microscopic particles rather than particles, energy threads that vibrate. Additionally, theory presents the notion of additional dimensions outside of the well-known trio of area, and sometimes these concealed sizes might be rolled up at such tiny scales that they nonetheless have undetected with the technologies available today. Loop is another notion that is gaining traction. Quantum gravity that aims to combine general quantum mechanics. According to relativity, space itself is quantized and composed of small, distinct, similar to a computer image's pixels. This perspective suggests that the Big Bang could not have been a real start, but more of a rebound from an earlier, collapsing cosmos. These substitute models that cast doubt on the traditional Big Bang theory story and provide fresh perspectives about the genesis of the cosmos and structure, but it's still rather speculative and devoid of comprehensive empirical confirmation that these are the cutting edge of contemporary cosmology. In the meanwhile, new observational tools are being improved, such as the James Webb Space Telescopes, JWST telescope, and future missions. For example, the Euclid Space Telescope, intended to investigate the early universe. In hitherto unheard of detail, they seek to catch the first star's brightness and galaxies, providing us with a better understanding of what happened just a few 100 million years after the Big Bang. LIGO and other gravitational wave detectors. Additionally, Virgo is opening a new window into the cosmos, enabling researchers to examine cosmic phenomena earlier. Even the hope is hidden from us that the next generations of these, the ability of detectors to detect gravitational ripples that come from the inflationary epoch itself, provides clear proof of the prevalence of inflation as we discover further information. The difference between conjecture and accepted science keeps changing, but cosmology is still one of the most active domains in all of science that combines mathematics and physics, imagination and philosophy in pursuit for fundamental truths at the core of the study of the cosmos. Involves more than only comprehending far-off galaxies, or it's about responding to the old light, most important issues in life. Where are we from, and what's the reality's essence, and where we fit in? Perhaps the universe doesn't have any tangible sign indicating the beginning of the universe is a subject of extensive research. The second is the best result in the end. According to current estimates, the universe will keep expanding endlessly. This is due to an enigmatic force called as evil energy that is in charge of the faster expansion of the cosmos. Prior to dark energy's discovery, according to physicists, the universe's eventually growth would slow down because to matter's gravitational attraction. There was perhaps a chance that the cosmos could cease to grow and start crumbling under extreme pressure. However, it seems that dark energy is increasing the distance between the universes fast. If this acceleration continues, the universe will continue to grow indefinitely, ultimately arriving at a stage where the distance between galaxies is so great that they grow apart from one another. In this scenario, the cosmos would cool off, the stars would burn away, black and empty. All matter and the universe would divide, fragment, and ultimately deteriorate as a result, referred to as freeze death or heat death of the cosmos. The narrative of the cosmos from the beginning to the end. One of the most deep is the potential end, and intricate scientific tales. While we have learned a great deal about the origins of the cosmos via the inflation theory and the investigation of the cosmic microwave background, there are still unsolved concerns about what caused inflation, what prevented it, and why exists outside of the visible universe. How many alternative multiverses exist? As scientists, we have universes. Keep exploring the cosmos, using ideas and cutting-edge technologies that blend quantum mechanics with. We will surely use general relativity. Find out more about these riddles by visiting the quest to comprehend the cosmos is continuous, and every new finding aids us come closer to providing the final inquiries about our existence. Examining the universe's structure and beginnings are, in addition to being a scientific undertaking, it also poses philosophical questions about reality, existence, and our role in the. One of the main topics in cosmology is the universe, is comprehending dark matter, which is believed to make up around 27% of the mass and energy content of the cosmos. Dark matter is not like regular matter, produces, reflects, or absorbs light, resulting in. It is undetectable and only discernible by its effects of gravity on visible matter. Learning about dark matter is essential to understanding the formation and recent galaxy dynamics. Observations and experiments have provided further details on the characteristics of dark matter, although its precise characteristics are candidates who are yet unknown. Have been suggested incorporating weakly interactions, large particles such as axions and WIMPs, but no concrete proof of dark matter particles. But the hunt is still ongoing, keeps going by combining astronomical experiments conducted on the ground, simulations and observations that simulate how the structure is affected by dark matter. In the cosmos, another vital region of dark energy is the enigmatic subject of inquiry. Power speeding up the universe's expansion. Dark energy is composed of about 68% of the mass of the cosmos energy content, and it was found to be surprising and has given rise to several explanations, as well as the cosmological constant, dynamic domains such as quintessence. It is essential to comprehend dark energy since it will decide the universe's destiny. Researchers are looking at how dark energy impacts celestial formations and if it stays the same throughout time or changes. In addition to dark matter, the investigation of energy and the creation of cosmic structures provides information about the universe's measurements of the cosmic web's history. Extensive system of galaxy clusters and filaments have shown the clumping of matter combined under gravity, resulting in the today's complicated structures. Supercomputer simulations are useful. Scientists are aware of how these over billions of buildings have been constructed countless years and keep changing. The intersection of cosmology and astrobiology. When scholars seek to comprehend the circumstances that sustain life beyond Earth and the hunt for extraterrestrial life outside of our solar system, circling stars has increased in the last several years, with thousands found. A few of these, their stars contain exoplanets, areas that are livable and where liquid water might exist. By researching these far-off places, researchers want to find out more about the possibility of life in other parts of the universe and its potential appearance. Moreover, physics is crucial function in cosmology. The pursuit of a cohesive theory that blends general quantum mechanics and relativity still poses a problem for physicists. Ideas such as loop theory and string theory. The goal of quantum gravity is to combine these two regions and maybe provide an explanation for occurrences like black holes, and the onset of the universe's technological advancements also enhance our capacity to perceive and understand space and cosmic phenomena, such as the James Webb Space Telescopes. Telescopes are transforming our comprehension of the cosmos by giving hitherto unheard before information about cosmic occurrences and far-off galaxies that, with every new observation, we progressively piece, putting the universe's puzzle together, creation, development, and ultimate destiny in. In summary, the study of the cosmos is a wide range of scientific investigation, as well as intellectual research, from the basic factors that influence cosmic structures to look for alien life and our search for knowledge is a reflection of humanity's profound interest in the universe. As we look for responses to these important questions, we not only gain new insights but further enhance our gratitude for the universe's size and complexity. The connection between observation and cosmology relies heavily on theory. Technical developments such sophisticated detectors using machine learning and Advanced algorithms are becoming better. Our proficiency in astronomical data analysis. Researchers may use these techniques to sort through enormous volumes of data, spotting trends that could indicate fresh perspectives on cosmic phenomena. One, a crucial field of study is ripples caused by gravitational waves in spacetime, brought on by disastrous occurrences like as black hole or neutron star collisions. These waves' discovery has opened a fresh perspective on the cosmos. Researching gravitational waves provides scientists' perceptions on the nature of harsh circumstances and gravity tests, theories using conventional techniques. In addition, the concept of cosmic time is fascinating in contrast to our daily view of time as uniform and linear. The universe's cosmic time is influenced by its expansion, which prompts inquiries about time itself. Is absolute by nature? Is it contingent upon the observer's motion and position? These philosophical questions follow scientific investigation that highlights the complexity of the cosmic. Examine how the first galaxies and stars referred to as the cosmic. Another crucial area of attention is daybreak. Knowing this epoch clarifies how the cosmos changed from a hot, fixed state to the intricate systems we see. The high redshift observations of today. Galaxies provide hints on the procedures that took place during this crucial moment, assisting scientists in establishing a cosmic evolution timetable.